I now want to calculate moments of inertia of objects with continuous mass distributions. No longer discrete masses. When we have discrete masses, then we can calculate the individual moment of inertia of the individual masses and add them all up. When you have a continuous mass distribution, you have to use an integral. You have to integrate over the entire volume of the object, and that complicates matters a little bit. And I will start with a classic simple example of using a rod with uniform mass distribution. I have here a rod. Mass is uniformly distributed. The rod has length L and it has mass m. And the mass is uniformly distributed. And I'm going to rotate this rod exactly about its center, about an axis which is perpendicular to the rod itself. So if this were that rod, it is a pencil, we think of it as a rod, then it would rotate about this axis, this vertical axis, to the middle of the rod. It could oscillate or it could rotate. In both cases, we would want to calculate the moment of inertia about that axis. Now, we have continuous mass distribution, so the moment of inertia, as we defined it, summed over all mass elements I times Ri squared, now obviously has to be changed into an integral. We have to integrate over this whole rod. I slice out here a small section dx. This is the axis of rotation, and this is at a distance x from the axis of rotation. I call this x equals 0. X would equals minus 1/2 L here. X equals plus 1/2 L here. What is the amount of mass that is in here? This little element dm, mass dm. Well, the fraction of the total mass that is in here is dx divided by L, and the total mass is m. So this is the mass of this little section which has length dx. And so if now I go to the continuous summation, which becomes an integral, then I get I will put a C in there to remind you that it is an axis through the center, now becomes an integral over x, and the x goes from minus 1/2 L to plus 1/2 L. I get m over L, and then I get dx, but I will wait with my dx because I have to multiply it with x squared. X is the distance from that mass element to the axis of rotation. So I get x squared, which is this term, dx. And this is a relatively easy integral. This is m over L times 1/3 times x to the third, evaluated between minus 1/2 L and plus 1/2 L, and you will find it not difficult, I hope, to convince yourself that this is 1/12 ml squared. This is a rather well-known result. When you look up the tables of moments of inertia, you can almost find in any book what the moment of inertia is of a rod which is rotating about its center. Axis of rotation perpendicular to the rod and uniform mass distribution. So I wouldn't even, if I were you, I wouldn't even try to remember this 12 ml squared. I certainly don't, but I want to show you that it can be derived in a relatively easy way.